we will briefly see about the pre-processing about medical images before we go into the classes. So
Medical image, DICOM images, madam.
yeah, it can be DICOM,
Or G.
JPEG, anything.
Okay.
It is applicable to any imaging format, sir.
Okay.
So I'll talk only about the general thing because you can adapt few of those steps in your project. So pre-processing of medical images is very important because it can improve the quality of the data, and also it can ensure that the deep learning model will perform well. So for these two reasons, to enhance the quality of the data and also for our model to perform better, we need to pre-process the medical images. We cannot straight away give the data. So there are certain key pre-processing steps because the steps will actually depend upon the imaging modality, whether it is X-ray, CT, MRI, or ultrasound. And also it will depend upon the specific task, whether you're using segmentation or classification, deduction. So based on the specific task and based on the imaging modality, the steps will vary. But today we will, in general, we will discuss what are the key processing steps available for it. So the first step is data acquisition and format conversion. So medical images are usually stored in DICOM. DICOM is digital imaging and communications in medicine. So it is a DICOM is a format in which most of the imaging data is saved. But these days we also save in other common imaging formats like PNG, JPEG, Nifty, and so on. So DICOM, it contains along with the imaging, it contains metadata also, patient information and acquisition parameters. So we can use, so if you are using Python, you can use PyDICOM to read the DICOM images. If you are using MATLAB, you can use DICOM read for reading the DICOM images. Am I audible now?
Yes, ma'am.
So what it will essentially do is that we need to convert the DICOM file into a common format before we are processing. So what this two functions will do is that it will convert the pixel values into grayscale. So, and also it will normalize the intensities and it will save in the imaging format, whichever imaging format you want it. So this is the thing. So first is we need to acquire the data and then you need to convert the format. So converting the format is changing the DICOM into PNG, JPEG, or Nifty. So these are the common things which is used. Otherwise, you need to, if you want to visualize DICOM also, you can visualize. Otherwise, you need to visualize in DICOM viewer to see the DICOM images. So this pre-processing is required if you need to convert DICOM into other formats. So the second thing which you will do is rescaling and normalization. Medical images, you know that they have different intensity ranges. So depending upon the imaging modality, it will have different intensity ranges. Rescaling will ensure that all of them are in uniform range and it will improve the model stability. So you need to convert into uniform range. This is rescaling and normalization. For normalization, there is a formula which you can use. So you find the maximum and the minimum intensity, and then where x is the intensity, x dash is the converted intensity, normalized intensity. So for every intensity, you find out the normalized intensity. So this is for every intensity, you subtract it with the minimum intensity, and then you divide by the difference between the maximum and the minimum intensity and replace it by the normalized intensity. So wherever
Voice is not audible, ma'am.
am I audible now?
Yes,
Hello?
madam. Yes, madam.
Yeah, okay. So, so if you took look at the whole image, in the whole image, you will find what is the minimum value and what is the maximum intensity value. Out of the whole pixels, you will find what the minimum and what is the maximum. And each pixel you will take, and then you will apply this formula, and you will replace each pixel value with the normalized value. So this is how, so that you have to run through a loop. So you have to run through the loop, and every pixel you will replace into a normalized value. This is how you will go on doing it. So ultimately your maximum value and the minimum value will be converted. So every pixel will be in the range of 0 to
Zero.
1 or -1 to +1. So this will be the first step which you will be after converting into the, what to say, after changing your image format, this will be your first step, which is normalization. For normalization, you have to use this formula. So you, while writing in the program, you will use a for loop to change every pixel in the image. There is one more formula, which is for z-score normalization. For z-score normalization, what you will need to do is that you have to center the data around mean is equal to 0 and standard deviation is equal to 1. This is nothing but standardization. The formula for that one is x is equal to mu by sigma, where mu is mean, sigma is standard deviation. For even for this one, so every, you will take in an image, you will take every pixel value, and every pixel value will be subtracted by the mean and divided by the standard deviation, and that value will replace the original value. So that is how you will uh, create the standardized image. And then you can also use histogram equalization. If you are using MATLAB, there is a command called histogram uh, so it will straight away create the equalized image. Am I audible now?
Yes, ma'am.
Hello?
Yes, ma'am, you're
Yeah.
audible, ma'am.
So, so histogram equalization is used for contrast enhancement, and it is useful in X-rays usually because it improves the visibility of these structures. But in other images also, based on the imaging modality, you need to decide whether you need to increase the contrast or not. So if you want to increase the contrast of the image, then you have to go for histogram equalization. And the third step is resizing the image and then resampling. So resizing the images, like for CNN, if you look at it, it will take the standard input size as 224 cross 224. So you have to resize the images to a standard fixed size. So that is called resizing, because some images can be 500 cross 400, 300 cross 200, or even 25 cross 25. So you need to bring all the images to a same size so that you can feed into your CNNs. So in that case, you have to resize it to a fixed size. For CNN, the size is 224 cross 224. So based on the imaging model you use, you can change your size. You will later understand in the class why this size is important, because for every model you have to give a particular size because your architecture will accept only that size. So in deep learning, the size of the images is also plays an important role. And then resampling. So resampling will ensure, like if you're using MRI or CT, resampling will ensure that there is consistent voxel spacing in the 3D images. So if you're using 3D images, then the voxel spacing for that resampling is important. So I don't think anybody is working in MRI and CT. If MRI and CT you are working, that you need to go for additional pre-processing. A lot of pre-processing is there for MRI and CT. If somebody is interested, I can discuss that privately with them. And then the fourth step is denoising and artifact removal. So every image modality has a different noise. So for example, if you take ultrasound, it has speckle noise. So if some other images, am I audible now?
Yes, ma'am. Now you're audible.
Yes. Now you are audible.
Okay. So if you are using MRI, you will have Gaussian noise. So if you use X-rays, you will have Poisson noise. If you use ultrasound, you will have speckle noise. So based on the imaging modality, medical imaging modality, different types of noises will be present. So what we need to do is that we need to come up with a denoising algorithm. So before processing the image, we need to remove the noise from those images. So for that one, so there are several methods for noise reduction. You can use if you are using MRA, you can use Gaussian blur. So there are straightforward lines. So if you are using Python, there is a straightforward code for it. So you can use cv2 dot Gaussian blur. So it will automatically remove the Gaussian noise present in it. So there is median filter both in MATLAB and Python. So you can use median filter to remove the salt and pepper noise. Even this is also good for ultrasound images. It can remove speckle noise from the ultrasound images. And then you can use wavelet transform for MRI denoising. And then the next step which we will see is data augmentation. Actually, denoising itself is a separate, it has been standardized, but before it was a separate research topic. You can develop a lot of denoising techniques. Pre-processing itself, you can develop as a separate research study. But now there are many standardized techniques. So we will use the standardized algorithms for denoising. And then the next is data augmentation. So what is data augmentation means? Increasing the data set size. So you are augmenting it artificially. So you're increasing the data size artificially because you want to improve model generalization. So suppose if the data is very less, with that you cannot come to a conclusion with the model. So what you need to do is that you need to increase the data set so that you can bring relevant conclusions in the model. So you can generalize the model.
Not audible, ma'am.
Ma'am?
Not audible, no?
Yes, ma'am.
Hello, am I audible now?
Yes, ma'am, you're audible, ma'am.
Oh. So there are a lot of techniques. Hello?
Yes, ma'am.
Yeah, okay. Sorry, today there is a lot of disruption.
Okay.
So flipping, contrast adjustments, and elastic deformations. So if in Python, if you use a term or if you use a command called augment, it will automatically create the augmented images. It is that simple. Augment bracket image. So in MATLAB, if you use if use im rotate, im flip. So there are techniques like that which will automatically what to say, create translations and rotations. And we have already provided you for MATLAB. We have already provided you. If you're using Python, you can use this one. So it will automatically augment your image, and it will create multiple copies of the same image with variations. So in that way, you can artificially increase the size of the data set so that a model will generalize better. So this will you will use whenever you are lacking the data, whenever you don't have sufficient data set, you have to augment your data set artificially. So for this is also an important step if you are considering to have more number of images in your model. Next, so if you are using MRI, then this becomes important. Skull stripping and organ extraction. So if you use MRI brain images especially, you need to remove the non-brain tissues to help to focus on the relevant structure. This is not only important in so this is not only important in MRI images, even in ultrasound images, you have to focus only on the structure inside the fan area. So you need to remove the structure which is outside the fan area so that your focus is only on the relevant details. So in MRI, we call this term as skull stripping for especially in MRI brain image. So you will look only into the organ of interest and you will not look outside the organ. So for a organ extraction, you can use organ segmentations. So you can use any deep learning technique for organ segmentation, or even a simple threshold based technique would work. Next, you have intensity standardization. So in intensity standardization, what you will do is that suppose if MRI scanners will produce varying intensity distributions, so you need to standardize those intensities across the scans. So you can use histogram matching for it. And then finally, as even not only in electronic health records, even here you need to split the data. So you need to have a balanced split. That is very important. So you have to have a balanced split for training, validation, and testing. So there are routines for doing this one. So automatically you can use train underscore split underscore train underscore test underscore split. It will automatically split the images into train and test. And also you can specify the percentage of it. So how much you want in train, how much you want in test. So it will automatically separate based on that one. So what we have seen so far is that we have been seeing the how to key steps in pre-processing the medical images. So the first what we saw is data acquisition. Data acquisition is nothing but how to read the image and convert into the imaging format in workable imaging formats. And then we saw about rescaling and normalization. Rescaling and normalization
Ma'am?
hello.
Yeah,
And
ma'am.
then we saw okay, and then we saw resizing and resampling. So this is standardizing the image dimension. This has to work with the image dimension. So we want to standardize image dimension before processing. And then we saw about denoising and artifact removal. So this is removing noise and artifacts. And then we saw about data augmentation. Data augmentation is increasing the number of data size. This is to improve the model robustness. And then skull stripping, it is extracting the organ of interest which we wanted to work. And then intensity standardization. Intensity standardization is normalizing the intensity distributions in the images. And then data splitting is splitting the data into training set, validation set, and test set. So this is the pre-processing steps, major pre-processing steps in any I'm not specifying any modality. For any medical imaging modality, these are the common steps. So you might need to have one or two steps more for your imaging modality, or based on the, or you need to use one or two steps less. So you have to choose based on your imaging modality. Is it clear? Any questions? So if you have no questions, then we will go on to the class. So what we did in last class, can anyone recollect what we did in the last class?
Activation function.
Yeah, activation functions. So what we did in that?
So linear for linear activation, we saw identity function, and for non-linear, we saw steps, stair step, unit step, heaviside, relo, leaky
Yeah.
relo, parametric relo.
So we saw different forms of activation function. So activation function itself is non-linear. If it is linear, it will collapse. The only place where it can be linear is at the output neuron. That is the only place where the activation function can be linear, because after that, after the output, no neurons are going to follow. So that even if it collapses, there is no problem. So the whole purpose of having the activation function is that it should not collapse. The network should not collapse. So it will include non-linearity. So our activation function itself is a non-linearity function. So we saw several forms of it. Today also we will see some of the forms of activation function before we go into the next interesting topic called backpropagation. So today, so last time we saw about some of the yeah, to continue, we will see some of the functions today. So we saw various form of ReLU functions. All these functions are nonlinear functions. They have multiple straight lines, using either having a bend or a curve or a kick, or in the they had multiple straight lines. So using different types, they became nonlinear. The alternative for that function is to have a smooth function. So previously we saw that it was bent, it was shifted. So we saw several types in that one. And we saw multiple staircase, unit step, we saw unit step, and heavy side functions. So there were all straight lines and the bent straight lines. So here, instead of having as a straight line, we will have it as a curved line. So we will have it as a smooth function. So if you look at it, so it looks just like ReLU. ReLU is like this, right? So if you look at here, this is also like ReLU, but it is in a curved form. So this is called as soft plus. So soft plus is the smoothened version of ReLU. So similarly, you have another function called exponential ReLU. So this is called exponential ReLU. It is nothing but smooth version of so shifted ReLU is something like this. So this is a smoothened version of the shifted ReLU. Another variation is sigmoid. So if you look at here, this is a uh, this is called as a sigmoid curve or a logistic curve. Or logistic function. So the name sigmoid comes from the resemblance because it is resembling a S-shaped curve. So while the other names refers to its mathematical function, this function is represented by its structure because it resembles S-shaped structure. I'm not drawing it perfectly. It will be like just like an S shape like this. So here it has the value of 0. So it has a value of 0 for very negative inputs, value of 1 for positive inputs. Between -6 to +6, it has a transition between 0 to 1. So in the range of between -6 to +6, it smoothly transitions between 0 to 1. So this is called a sigmoid curve. Sigmoid curve has 0 value for negative values, 1 for positive values, and it is transitioning between -6 to +6. And this range can vary. It is not always fixed. -6 and +6 is not always fixed. The range can vary. So here, for example, I am taking it as -6 to +6. So this is, but to see, it will look like an S-shaped curve. So closely related to sigmoid is another mathematical function called hyperbolic tangent. So it is hyperbolic tangent is also called as tan h. So if you look at here, this is also a S-shaped curve. So tan h is also similar to sigmoid, but the range is varying from 1 to -1. Here it is 1 to 0. Here it is 1 to -1. So here also it has negative values for negative values of x, it has negative values. For positive values of x, it has value of 1. So it has a values of -1. Here it has values of +1. So between -6 to +6, it varies from -1 to +1. So what is the difference here and here is that the transition region is very narrower here. It is -6 to +6 here, but here it looks maybe from -3 to +3. So the transition zone is very bit narrower here. So we can say that both sigmoid and tan h functions are squashing the entire input range. Here it squashes the input range between 0 to 1. Here it squashes the input range between -1 to +1. So, so you can draw both the functions like this. So you can see how it squeezes. Uh, this is tan h function. This is sigmoid. While the tan h squashes its values between -1 to +1. So the combination of, you can have combination of these shapes. So there is one combination you can look at it. It is a combination between Rayleigh and sigmoid shape. It is called as swish shape. So what is our Rayleigh? Rayleigh is 0 for negative values and the input follows the output in the positive side. So that is Rayleigh. Sigmoid is, there is a transition between 0 and 1. So that is sigmoid. So here it is a combination of both. So combination of Rayleigh and sigmoid. So this is called as switch. So it is essentially a Rayleigh, but with a small bump just left to the zero or zero. It has a small bump and then it flattens. So this is switch activation function. It is combining Rayleigh and sigmoid. So Rayleigh is the most popular one But if you are looking for the real derivative of the activation functions, then sigmoid and tan H are the preferred choices. So the downside of the smooth curve, so far we have been seeing about all these are smooth curves. So the downside of the smooth curve is so anyone can guess what is the downside of the smooth curves?
There's
Hello?
no sudden transition is happening in.
Fantastic. Excellent. So the downside of the smooth curve is that it can produce useful result only in the narrow input range. So if you look at here, so only in the narrow input range, it can produce useful what to say inputs. In this side also, it is getting saturated. So for example, like what to say, when the input gets larger than 6, when the input is larger than 6, or or when the input is lesser than -6, what will happen? It will give us the same value. It will give 1, or it will give 0, or it will give -1. So the phenomenon is called as saturation. So the when the output is always the same value, the derivative of the function will become 0. So when output is constant, there is whenever there is change in output only, there will be derivative. If the output is constant, the derivative is going to be 0. So you might ask, this condition is also seen in ReLU. So before that, we will write this one. So you might ask, so this is not the case even in ReLU if you look at it. So let's take this one. So even in ReLU, the negative side is saturated. Only in the positive side, the input follows the output. But here it is saturated. So it will, even in the negative side of the ReLU, we will have the same problem because it will always return 0 for all negative values. So it is saturated. But in the positive side, it is not saturated. So people use this one. But in here, both the positive and the negative side, we have saturated values. So the derivative can become 0. So that's the reason we have variety of activation functions. So we can use multiple activation functions. In theory, there is nothing called like which will work best. We have to try it out. We have to try different one of them and see which works better. And then we have to choose based on that one. So this is the activation function. We will see about one more activation function, which is called as a softmax function. Am I audible now? So this softmax function is usually applied at the output of the neurons. So it is usually applied at the output of the neurons of the neural network classifier. It is not an activation function. But it is applied to all the output neurons. Not just one output. For every output, the softmax is applied. So this we often use this in the final step of the classification networks where we have multiple outputs. We call this as softmax activation function because mathematically it is similar to activation function, but this technique is not an activation function. So what is the purpose of softmax function is it turns raw numbers into class probabilities. So that is what it will do. So let's take one example where we have 3 output neurons. So you get from the rest of the network, you get weighted inputs for all these 3 output neurons. This is the rest of the network. So all these outputs goes to the softmax function. So every output will produce a score. So output is nothing but the weighted sum of the inputs. So it will produce one score called A score. This will produce another score for B score. This will produce another score called C score. So similarly, so the softmax, what it will convert. So we saw that the softmax converts raw numbers into class probabilities. So here you are giving these scores to the softmax function.
You're not audible, ma'am.
Am I audible now?
Yes, ma'am.
Yes, ma'am.
So what here the softmax does is that, so we will get a score. Till that is, sorry, today there is a lot of signal disruption, so we are not able to follow. So till that, is it clear for you? So here we have our network. So the network has three output neurons, A, B, C. So it has three output neurons. These output neurons, so it will get input from the previous neurons from here. So all these previous neurons will give their corresponding input to the output neurons. So this output neuron will combine all these inputs and produce an output. So this output will have one score. So every output will have one score. So here corresponding to A neuron, A score, B score, C score. So three scores are produced based on the output neurons. And then it was given to a softmax. So the purpose of softmax, what we saw here, it converts raw numbers into class probabilities. So it will convert the score into a probability. So corresponding to A score, we created probability of A. And then corresponding to B, we created probability of B. Corresponding to C score, we created probability of C. So here we have three categories, A, B, C. So for each of the three output neuron gives us a score. Am I audible now? Hello?
Yes, ma'am.
Yes,
So,
ma'am.
yeah. So, so why we have three scores is that, so suppose if you are doing a classification problem, so you have to classify whether it is a dog or a cat or a horse. So let us name this as class A, class B, and class C. You are giving a cat picture. So each one of them will get a score. For example, dog will get 85%. Sorry, not percent, 85. Cat will get 200. Horse will get 10, for example. So seeing this score, you can see. So cat has a largest score. So the input image is cat. So the B has the largest score. The B score is, A score is this one. C score is this one. So what you are doing is that you have a network. So for the network, you are giving your input, and the input and the network will process it, and it will produce three output neurons are there. So corresponding to three output neuron, three scores are produced. A, B, C, three scores are produced. So whichever has the highest score, that will be the output of the network for the particular input. For this input, so the score is B. Score B has a largest score, so that corresponds to cat. So that is the output of this particular input. So this is how we will classify. So now instead of giving these scores, we are giving these scores to a softmax function. So this is what is happening here. So here we are giving these scores to the softmax function. This softmax function will convert this one into probabilities. So here, for example, it will create for 85, it will create the score as say 0.3. So for this one, it will create 0.6. For this one, it will create 0.1. So three scores it is creating. So A has a probability of 0.3, B has a probability of 0.6, C has a probability of 0.1. So now you can say that uh, B is twice time probable of A. B is twice times as probable as B. And it is B is 6 times more probable than C. You can say that B, otherwise you can say that A is 3 times probable than C. So we can make this kind of statements like we can make these kind of statements when it is in probability. Sorry, today there is too much of disturbance. I will try to wind up soon. So if you look at here, so here it is a probability. So the probability means every probability should add up to 1. So 0.3 plus 0.3, 0.6 plus 0.1 is 1. So all these things should add up to 1. But here, if you take the score, it will not add up to anything, either to a percentage or to 1. This is 85, 210. So it doesn't make sense. So here you can compare when it is adding up to 1, you can compare it easily, like B is twice the times of A, B is 6 the times of C. So this much probable it is. A is 3 times probable than C. So you can compare each of the outputs. So that is possible with softmax because it is converting the score into a probability class. So next time when somebody asks what is a softmax means, it is an activation function which is converting the score into a probability class. So, and one more important thing is that it is not doing it individually. So all the scores are given it together. Then only it is converting here because we need to add up all the scores because since it is a probability, all the scores should add up to 1. So if you do it individually, then we cannot do it. So we need to do it together. So all the output should be given to the softmax. Then only it will convert into probability. You cannot give individual things and it cannot work on the individual output score. It has to be given to the combinedly given to the all the scores. Am I audible? Hello?
Yes, ma'am.
Yeah,
Yeah. Sorry, there is a lot of disturbance today. So this is what it is. with this we conclude activation function. From next class onwards, we will work on back propagation. So back propagation is nothing but how the network learns. So far we have been telling that. So whenever there is an error, the network will has to learn by itself. So how the network learns, what the network learns. So that is the most interesting concept in deep learning. So we will start with back propagation from next class. So in today's class, what we did is that we saw the important component of pre-processing the medical images. So we saw the key processes involved in the pre-processing of medical images. And then we continued with the forms of activation functions. So far we have been seeing only about the multiple straight line functions. Today we saw about the smooth functions, the modifications of ReLU, modifications of shifted ReLU, and about the S-shaped curve, that and the variation in the S-shaped curve, which is a tan H function. And then we saw the combination of ReLU and sigmoid. And we also saw what is the downside of the smooth functions. And we also described about the most important function, which is called as a softmax function. Softmax functions is usually provided at the output of the neurons. It is not an activation function, though it is mathematically similar to an activation function. It is not called as an activation function. Here it is used to convert the raw numbers into class probabilities. So when we are giving that, we need to give the combined score. We should not give the individual. It will not work on the individual scores. It will work on the overall score. So we have to give all the scores of the output. So all the output should be given to the softmax to convert into the probability. So this is what it is. So any questions?
Just one thing that, so actually what you told was all this ReLU and all are weightage is given to the two different types that you give. Whereas softmax is a post analysis. Like, I mean, you isn't it's
Yeah.
is it
Mm, yes, ma'am.
is it what I'm understanding is correct?
So ReLU softmax is given at the output. ReLU
Out
is given at the inner layers.
inner layers and more like an input weightage, everything, those crisscross you
So
did.
what it will do is that here it is providing, as you say, it is like a filter. So
Okay.
so it is like a, suppose you have your output here and it
Ah,
is passing through ReLU.
yeah. Hello. Cut out.
Uh, and so so suppose it has a value or output of -5. So it
Ah,
will go to ReLU. So
ah,
it will check where this -5 falls. -5 is less than 0. Less than 0 means output is 0. So suppose
oh,
if the output is +5, so
ah,
it will check +5 is in the positive region. Positive means whatever is the input, that will be the output. So output is 5.
oh, okay.
So this is how it will convert there. So that is why we are using the functions. So these graphs are saying how it is converting input into output. So what happens on the negative side, what happens on the plus side.
Whereas softmax is the output with relative to the other, the various.
So so
Ah,
softmax is when the output comes. So you have your softmax here. So what
mm,
it will do is that it will, suppose it has a score 5. It will
mm.
convert the score into a probability, 0.5 or 0.7. So it is converting score into probability.
Right, right, right. So it's a output data. I mean, not data, it's an output function. Or what?
Yeah, it's
Not
an
a,
output function,
yeah, right. Yeah, got it.
but it is mathematically similar to it. So it is called as an activation function, but it is not doing the job of, it is not there to include non-linearity, whereas ReLU is there to include non-linearity here. But here,
Yes.
this is there to convert into class probabilities. So that is the
Okay.
difference.
Yep. Thank you.
Okay, any questions? So if you have no questions, then we will see in the next class on Friday. Thank you.
Thank you. Very nice class. Thank you.
Thank you, ma'am.
Thank you.